Welcome to Algorush. Today, we're going to dive into one of the most fundamental, yet pretty much invisible, building blocks of our digital world. Seriously, it's the reason our systems are so fast, and without it, well, your online life would look very, very different. So just think about it for a second. We are absolutely drowning in data, trillions upon trillions of bytes. So how on earth does any system manage to sift through all of that noise to find the one specific thing you're looking for, and do it, instantly?
Well, the secret isn't just about having faster hardware or more processing power. No, it's something way more clever. It all comes down to structure. See, data isn't just dumped onto a disk randomly. It's meticulously and really intelligently organized.
And the most fundamental unit of that whole organization is something called a page. Probably the easiest way to picture it is like this. Imagine an entire data file is a massive, massive book. Well, that book is broken down into these fixed-sized chunks, these pages. And that simple idea right there is the key to everything. So to really get how this works, we've got to zoom in. Let's peel back the cover and take a look at the actual blueprint of a single one of these pages. Okay, so every single page starts with what's called a header. Now, this isn't your actual data. Think of it more like the page's instruction manual or its table of contents. It has flags that describe what's on the page, a running count of how many records or cells are stored inside, pointers to where the free space is, and even special pointers to other child pages. It's all the metadata the system needs to make sense of what's coming next. And tucked away inside that header is this really neat little trick for making sure everything is okay. A magic number. It's just a constant, unchanging value that acts like a secret handshake. When the system reads a chunk of memory, the first thing it does is look for this number. If it's there, great. It knows this is a valid, uncorrupted page. If it's not there, that's a huge red flag that something's gone wrong.
So what about the actual data? How is that stored? Well, the records themselves, the cells, they're just tacked onto the end of the page as they arrive. They can be in any old order. But here's the genius part. A separate list of pointers, which are really just addresses showing where each cell is kept near the beginning. And that list is always kept perfectly sorted. And why do that? Because it lets the system use a lightning-fast binary search to find any pointer instantly, no matter how messy the actual data is.
Now, this system is incredibly efficient, but it does bring up a pretty obvious question. What happens when you've got a massive piece of data, like a really high-resolution video or a huge document, that is just too big to fit on one of these fixed-size pages? And the solution for this is actually pretty elegant. The system uses what are called overflow pages. A chunk of the data lives on the main page, but the rest of it just spills over into a linked chain of one or more of these extra pages. This is great because it keeps that primary page structure super clean and fast, while still letting you store data of pretty much any size you can imagine. Okay, so we've got headers, magic numbers, sorted pointers, overflow pages. I mean, that is a lot of complexity to pack into one tiny little page. So the big question is, why bother? Why does all this intricate structure actually matter? It all comes down to one thing: the physical reality of how computer storage actually works. See, jumping around the disk to grab different pieces of data, what we call random I/O, is incredibly slow. It's like trying to find 100 random words in a dictionary. You spend all your time just flipping back and forth. But reading data that's all in a row, sequential I/O, is like reading a chapter from start to finish. Once you're there, it's blazing fast. The difference in performance isn't small. It's absolutely astronomical. And that, right there, is the entire point. The whole page structure we just walked through is engineered specifically to work with the hardware, not fight against it. The whole design is about one thing: avoiding those painfully slow random seeks and maximizing those super fast sequential reads by loading data one organized chunk, one page at a time. And when you really step back and think about it, you realize that this one single, highly engineered page is the invisible foundation of our entire digital world. It's this tiny microscopic blueprint that makes massive high-performance applications, from your social media feed to the global financial markets, even possible. And what's really cool is that this page blueprint is just one elegant solution out of many, which kind of makes you wonder, what other invisible structures, what other hidden architectural marvels are out there right now, powering the digital world?